Hi everyone, welcome to my video on elementary differential equations. This will be video number 20 for chapter 3. We will study some applications of the initial value problem of the second order linear equation of the following form: a y double prime plus b y prime plus cy equals some function of t. Here a, b, and c are given constants, and initial conditions are given at t equals 0. So y at 0 is given, that's y naught, and y prime at 0 is given as y bar naught. The application we will focus our attention on is the mechanical vibrations. We will take the spring mass system as our main focus of the applications. So let me explain the system in some detail. So here I have some drawings of this system. Let's start from figure A. What is stated in figure A is, so on the top from the ceiling, it's fixed the end of a spring, and the spring is naturally hanging there without carrying any weight on the other end. So a spring is, we call, in rest. And let's say in this state, the spring has length, which is denoted by L. Okay, so in figure B, what happens is that we now take a mass with the mass m, we hang it on the lower end of the spring. Then from experience we know that due to the weight of this mass, it would pull the spring down and the spring will be stretched. And let's say the amount the spring is stretched is capital L. And this capital L is called the elongation. Then without disturbance, the system here is at rest, and the elongation L is the elongation where it reaches an equilibrium. Okay, now we excite the system, which is depicted in figure 3. We can set it in motion by disturbing the position of the mass by either stretching it down further or squeeze it a bit upwards. And then we can either let it go with initial velocity or without. Or we can even add external force in time to keep it in a certain motion as we desire. Okay? Then if you take a snapshot of the system at a certain time when it's not in equilibrium, it would have, for example, an extra stretch, which is depicted here. So it's moved away from the equilibrium. The amount it moves away is the extra stretch. Let's analyze the force that is applied on the mass. So we draw the force diagram. Let's first look at the force when it's in the equilibrium position. That is, the mass is not moving. So if it's not moving, then that means the total amount of the force will be 0, right? So what kind of a force does the mass have? Okay, so the first one is the gravitational force, which points downwards, is pulling it down. And this force is m times g, where the g is the gravitational constant. And then there is a force from the spring because it's stretched and the spring is pulling it upwards. Therefore, this mass is going up. And we call it capital Fs to say that's the force from the spring. That's, in this case, if it's stretched, and then the force goes upward. Now if it is at an equilibrium for the mass, then the total force shall be 0. That means how much is pulling it down must match how much is pulling it up. So mg equal to F sub s. Now we introduce the Hooke's law for the spring force. So what is the spring force? So the spring force equal to negative K times L, where this L is the elongation, and then K here is some constant. We call it the spring constant. So depending on your spring, K can be different. So what this says is that the force exerted from the spring for a given spring is proportional to the elongation. If you stretch it further, it pulls you more strongly backwards in a linear relation. Okay? And then for different spring, the spring constant can be different. Okay, so an important comment we want to make is that the spring constant actually can be easily computed. That is, you can hang a mass of mass m over there and find out the elongation, which can be measured. Then we have mg equal to kl, and use this, we can compute the k, the spring constant, that will equal to mg over L by simply divide both sides by capital L. Okay, so this relation here tells us a way to obtain the spring constant by this simple experiment. We now look at how to set up a mathematical model for the motion of the mass that's hanging on the spring. So let's define the quantity that we will be studying. So we call this U, and stands for unknown. The unknown U of t will be the displacement or position of the mass at time t. Okay, and you have to assume where is the origin. So assuming that we can put the origin U equals 0 at the equilibrium position. And then we assume also downward is the positive direction. So this direction, the positivity of the direction, is a choice. You can choose upward. Then you have to be consistent in your modeling, and you have to remember that point upwards is positive. Okay, so with this definition of an U, then we know that the total elongation of the mass of the spring would be the elongation at the equilibrium L plus the U, that's the further elongation. And the total spring force we can calculate, F of S, would be negative K times the total elongation, which is capital L plus U. Okay, let's also add some other forces into consideration. One is called the damping force, which is also known as the resistant force. This is a force that goes in the opposite of the direction of the movement. It could be air resistance, or if your motion is in a fluid, then the fluid is having a damping effect on you. Okay, so we call it Fd, and this is equal to a negative gamma times v. V is the velocity, which has the direction. So it's in the opposite direction of the v, therefore there is a negative sign here, and gamma is a constant which is multiplied on the v, so that the resistant force is proportional to the velocity, but in the opposite direction. Okay, and then we also know that the velocity is the derivative of the position or displacement. So it's u prime we can put in here. So we have Fd equal to negative gamma times u prime. The second force we consider is a possible external force being applied on the mass. You might be pushing it with your finger or pushing it with a stick or some other forms. It could be a function of time. So we just put it in a general way. So it's a capital F of t. So it's just a given function of t. And if f of t is positive, that means the force points downward. If it's negative, then the force points upward. Okay, so with all these forces being taken into consideration, then we can add up the total force on the mass. So summation of all the forces would be mg, the gravitational force, plus the spring force. Here we already take into consideration of the negative sign here, which is given there, and then the damping force, which we talked about at this step, and then the external force being applied on the mass. Then to study the motion of the spring mass system, then we apply Newton's law of motion. Newton's law of motion says the acceleration times the mass would equal to the total force on the mass. Okay, so let's put in each term then. So the acceleration, m times a, is the derivative of the velocity, and the velocity is the derivative of the position. Therefore, the acceleration is the second derivative of the position. So m u double prime would equal to total force. Total force we just talked about earlier is mg plus fs plus fd plus external force. Okay, so let's remove the unneeded terms and extract the important information here. It says m of u double prime equal to this, where we plugged in each term. So mg, and the spring force is this term here, and the damping force is this term, and the external force. So what do we get? Well, we get a differential equation for the unknown u. So this equation contains constants which are given and contains the unknown u. U appears in itself and in the first derivative and in the second derivative of itself. Okay, and we see that a little simplification can be made in this equation, because we know that mg equal to kl, because that's how you could compute the spring constant, right? So if that is the case, then if you distribute the k into two terms, then the negative kl will cancel the mg. So that term is gone. Okay, and then you can move all the terms containing the unknown u to the left-hand side. So I will get m u double prime, and then negative ku move to the left, become positive ku, and then negative gamma u prime move to the left, become positive gamma u prime, and then that equal to what remains on the right hand side, and that's the external force term. Okay, so I put this equation in red because that's very important. That's the equation we derived, and we'll be studying various solutions of this equation in various cases. Okay, so we have the spring mass system, which is given here. Let me block it, and that's the differential equation, and the meaning of each term are the following. The m here is the mass, remember, the gamma here is the damping constant, and the k here is the spring constant, and the f here is a function of t on the right hand side. That is just the external force term. Okay, so in this video we derived this differential equation. So looking at it, we see that this is a second order differential equation with constant coefficient, but with the right hand side term not zero, so it's non-homogeneous. Okay, and in the following videos we'll be discussing different solutions of it and connect them to the physical meaning of these terms, and then towards the end the effect of adding external force. Okay, so I hope you enjoyed this one, and I look forward to see you next time.